Okay, welcome back to astronomy. Today we're going to take a little detour, a little sidetrack from talking about stuff in space and talk a little bit about really particle physics. Why are we doing that? Well, one of the reasons is that I'm a particle physicist and I like talking about particle physics. And the way, sorry for a second, I'm going to get this thing that I put under my monitor or under my laptop. Recording a video and it makes the angle better, right? That makes it better. I'm a particle physicist by training. My PhD is not in astronomy, it's in physics and particularly theoretical particle physics. So I know a lot about this stuff. But the kind of professional entry point for me into astronomy is through particle physics. One of the things that I find fascinating about the connection between astronomy and cosmology and particle physics is you wind up, when you're studying astronomy, coming face to face, which, by the way, studying astronomy and cosmology is studying the biggest things that exist in the universe, right? You wind up inevitably coming face to face with questions about the smallest things in the universe and vice versa. If you start asking questions about the smallest things in the universe, you wind up inevitably coming to the point where we're asking questions about the universe as a whole. So that's super interesting. The other reason to talk about this is one of the things I talk about a lot in this class, or try to talk about a lot in this class, is evidence. How do we know these things about stuff in space? How do we know that the sun has nuclear fusion going on in its core if we can't see the core of the sun? If we only see the surface of the sun, and the surface of the sun isn't hot enough for nuclear fusion to go on? How do we know that process is really the thing that we talked about in the last lecture? Well, this is one of the ways we know. I said that, oh, sorry, this, we'll come back to a slide like this. This slide is moving for no reason. We talked about the fact that in the process of nuclear fusion, the first step involves two protons colliding and turning into a proton and a neutron, or deuterium nucleus. So at some point in this process of transformation of hydrogen into helium, some protons have to turn into neutrons somehow. And I said that you can think of a proton as being able to, quote unquote, turn into a neutron plus a positron, an anti-electron. That's not exactly what happens. There's this other particle that's given off. This fact was discovered in the early part of the 20th century. 1930s is when we were doing the research. 30s and 40s is when we kind of proposed the solution. Looking at radioactive decay. This is a process called radioactive beta decay, which is a process where a neutron turns into a proton and it spits out an electron. That electron is sometimes called a beta particle, or was called that back in the early part of the 20th century, before we kind of knew what electrons were and what they were doing in atoms. So here's a process where a carbon-14 nucleus, carbon-14 is 6 protons and 8 neutrons. That's a radioactive isotope of carbon. Normal carbon is carbon-12, 6 protons, 6 neutrons. Carbon-14 is radioactive. You might have heard of radiocarbon dating or carbon-14 dating. That is a process that we can find out how old something is, something made of organic material, by measuring the amount of radioactive carbon-14 in it. Radioactive isotopes are present all around you all the time. Most of the carbon in your body is carbon-12, but like 1 in a million carbon atoms in your body is a carbon-14, and it's a little bit radioactive, and it's fine. There's stuff that's a little bit radioactive around us all the time. When carbon-14 decays, it decays by a process called beta decay, where one of the neutrons turns into a proton. So its atomic weight stays 14. There's the same number of particles in the nucleus, but instead of carbon, now it's nitrogen, because instead of 6 protons, there's now 7, because one of the neutrons turned into a proton. So carbon-14 has 6 protons, 8 neutrons. Nitrogen-14 has 7 protons, 7 neutrons. That's the stable isotope of nitrogen. This is all more detail than you need to know. Suffice it to say, there's a process called beta decay. And when scientists were experimenting with radioactivity in the early part of the 20th century, they found that in this process, there was less energy in the resulting nucleus, even if you count the energy that the electron leaves with, than we started with. Now you might say, well, that's not okay, right? Isn't there a law of physics called the conservation of energy? Yes, absolutely, there is. If science really worked the way the posters in your middle school classroom told you that science worked, where you do an experiment, you have a hypothesis, and you do an experiment, and if the experiment doesn't support the hypothesis, you throw the hypothesis away and make a new one. If science really worked that way in practice, if it was really that simple, and you did an experiment and you found that energy wasn't conserved, you would say, oh, well, I guess energy isn't conserved. We'll throw away that law of physics. That is not how it works. That's not what anybody thinks in the real world about science. More often, if an experiment doesn't turn out the way you thought, there is some other effect you didn't know about that affected the result of that experiment. I'll give one example from astronomy. In the 1700s, the late 1700s, we discovered the planet Uranus with a telescope. You can't see it with the naked eye, so we discovered it. And then we, over the next several decades, plotted its motion through the sky and its orbit and tried to calculate its orbit and found out that it wasn't moving in the path we expected it to move. If we calculate the force of the sun's gravity on Uranus and calculate the orbit it should be following, it wasn't following that orbit. What did we do? Did we say, oh, I guess Newton's laws of gravitation must be wrong or they don't apply to Uranus? Of course we didn't say that. What we said is there must be some other effect we're not seeing, we're not taking into account when we measure its motion. What was that effect? Well, what could it be? Maybe there was some other planet out there exerting a gravitational pull on Uranus from the other direction. And we figured out where that planet would have to be, and we pointed our telescopes there and we found Neptune. We went looking for Neptune because Uranus wasn't doing what we expected it to do. So we believed Neptune existed for many years before we actually found Neptune. Here is a parallel on the much, much smaller scale. We do this experiment with nuclear beta decay. We find that the energy after the decay is less than the energy before the decay. Is that allowed? Conservation of energy says that's not allowed. What do we say? Do we say conservation of energy is wrong? No, we say there must be some other thing with some energy in this system that we didn't see or didn't detect or haven't discovered yet. We named this thing the little neutral particle or neutrino. We know it has to be neutral because all the charges is accounted for, right? A neutron turns into a proton plus an electron. So zero charge, positive charge, negative charge, zero charge, all the charges work out. So whatever this thing is, it has to be electrically neutral. It also has to be tiny because the amount of energy missing was tiny, tiny, tiny. It also has to not interact with things like particle detectors and Geiger counters, or else we would have detected it. So we proposed, actually the worst person who proposed this was Wolfgang Pauli in the late 30s, early 40s. That in the process of turning a neutron into a proton or a proton into a neutron, there are these other little particles involved called neutrinos, little neutral particles. And it wasn't for a decade or so that we actually built an apparatus to discover them. How do you discover a particle with no electric charge that isn't picked up by a Geiger counter or radiation detectors? It's hard. Neutrinos are very hard to detect. And the reason they're hard to detect is because they're electrically neutral. If we think about what happens in the macroscopic world when things collide with one another, what happens when I bang my hand against the desk? Why doesn't my hand go through the desk? Why does it just stop? After all, atoms are mostly empty space, right? If we made a model of an atom and this ping pong ball was the nucleus, the electrons would be, this would be like if I stood on in a football stadium with this ping pong, this is a golf ball, not a ping pong ball. If I stood with this golf ball on the 50-yard line of a football stadium, the seats where the crowd is would be where the electrons are. And then all that empty space between the nucleus and the electron is just empty space. And then there's more empty space and then another atom and then more empty space and then another atom. So atoms are mostly nothing. They're tiny, tiny little particles in empty space. Why then, if atoms are mostly nothing, when I hit my fist against the desk, doesn't my fist go right through the desk? Well, because what's on the outside of my fist's atoms are electrons, and electrons are negatively charged. And what's on the outside of the desk's atoms are electrons, and electrons are negatively charged. And when my fist gets close enough to the desk, the electrical repulsion of my electrons and the desk's electrons keep my hand from moving any further. My hand is never actually touching the desk at the microscopic atomic level. What would that mean? That would have to mean that some of my electrons are touching the desk's electrons. That's impossible, because if two electrons were touching, the force between them would be infinitely big. Electrons can't touch each other. They can just get so forced that their electrical repulsion is pushing back harder than the force pushing them together. So what happens in the macroscopic world when things collide with one another is actually electrical repulsion. The reason my fist can't go through the desk is that it's electrically charged on the outside of all of its atoms. If my fist was made of pure neutrons and had no electrical repulsion, I could just put it right through the desk because there would be nothing to stop it. That's what neutrinos do. They go right through stuff because they're not electrically charged, and they don't interact by the usual electrical interactions between charged particles or nuclear interactions between protons and neutrons. But they have to interact somehow, because if they don't interact somehow, they wouldn't be created by any process. There has to be some interaction between neutrinos and protons and neutrinos and electrons, or this process that creates them couldn't happen if there was no physical connection between those particles. So there has to also be some other force of nature, some force of nature that is not electrical attraction and repulsion, not the strong nuclear force that holds protons and neutrons together, but some much weaker force that governs the interaction between neutrinos and electrons and the quarks inside of protons and neutrons. Physicists have cleverly dubbed this weak interaction the weak interaction. So the forces of nature are electrical attraction, repulsion, gravity, the strong nuclear force, and the weak nuclear interaction. And the weak nuclear interaction is the only force that neutrinos feel. If neutrinos are created every time a proton turns into a neutron or a neutron turns into a proton, that means the sun is making tons of neutrinos all the time. And those neutrinos will be flying out in all directions every time a proton is fused into a neutron in the core of the sun. Trillions of times a second, there will be a neutrino made. Those neutrinos fly out into space, and some of them should hit the Earth. The Earth is far away, so it takes a while to get there. Are we at the Earth yet? We got to do 93 million miles. There we go. Now we're at the Earth. Some of those neutrinos from the sun should reach the Earth. What will they do when they get to the Earth? They will go right through it most of the time. Why? Because they're electrically neutral. They don't feel electrical repulsion, so they're not stopped by electrons. They don't feel the strong nuclear force, so they're not stopped by protons. They will go through the Earth unless they interact via the weak interaction, which is weak, so it doesn't happen very much, with an electron or a proton. If you draw a square in your hand, on your hand, that's 1 inch by 1 inch by 1 inch, and you go outside and you hold your hand up to the sun, there are trillions of neutrinos every second passing through that square, passing through your head, passing through the ground, and then coming out the Earth on the other side. At least that's the theory. These tiny, invisible particles that we didn't even know about until the late 40s, early 50s, are going through your body all of the time and going through the Earth and coming out the other side. How do we know this? We build big, giant detectors to detect them. How would you detect a neutrino if it doesn't interact with electrons or protons via the nuclear interaction? Well, you just have to wait a long time for one of them to interact via the weak interaction. You just get a bunch of atoms and you put them in one place and you wait for this interaction to happen. What are you looking for? You're looking for, say you got a bunch of hydrogen, okay? Proton, one electron, that's hydrogen, right? You got a big tank of hydrogen and some neutrinos come through your tank. Most of the time they just go all the way through and nothing happens. But every once in a while, one should experience a little bit of force via this thing called the weak interaction. Let's just say it interacts with an electron. What happens? The electron experiences a force, the neutrino experiences a force, the neutrino bounces off, and the electron bounces off just like it was hit by an invisible billiard ball. So we don't actually see the neutrino. What we see is an electron go zipping off that got its energy from something we didn't see. When that electron moves off, we can detect the motion of the electron. How does this work in practice? Usually what we just use is water. Water is mostly hydrogen, right? H2O. Most of the atoms in water are hydrogen atoms. There are a bunch of electrons just hanging around. Every once in a while, if we get a big enough tank of water, one of them will get a little kick from a neutrino and it will fly off through the water. And when it does it, it gives off a little flash of light from its interaction with the other electrons in the water. That light is called synchrotron radiation, or Cherenkov radiation, actually. And we detect that light. So the easiest kind of neutrino detector to build is just a big tank of water with light detecting sensors all around it. And what we do is we just wait and wait for the detection of a little flash of light that represents an electron zipping through our water that was given a kick by something invisible. Now, how do we know that kick was a neutrino and not something else, just random radioactivity? Well, what we do is we build this tank of water deep underground, so none of the cosmic rays from space can get into it. And we shield it with metal, so none of the radioactivity from the rocks can get to it. So the only thing that can get to this underground tank of water is a neutrino that can go right through the Earth and right through that shielding and get to our tank. Here is a picture of one of those detectors from the inside. You can see the water. You can see the shiny sensors are light sensors. And to get a sense of the size of this thing, this right here is two guys in clean suits in an inflatable life raft. And what they are doing is cleaning the light sensors. So they fill it up with water, they clean the light sensors all the way around, then they fill it up with more water, and then they clean the light sensors all the way around. So they're just servicing this neutrino detector. I think I've got a bigger picture. This is a neutrino detector called Super Kamiokanda. It holds 50,000 tons of water. You can think of it as being kind of an Olympic-sized swimming pool in the shape of a cylinder that's as deep as it is wide. And it's surrounded by 11,000 phototubes or photosensors, just light sensors. And here again, this is 2 or 3 technicians in an inflatable life raft servicing these phototubes. And this is built in an abandoned mine, abandoned salt mine, I think. So it's hundreds of meters below the Earth's surface. And we turn out the lights and we wait. And what we find when we do this is we detect several dozen neutrinos every day, several dozen flashes of light that correspond to neutrinos, banging into electrons, sending them zipping through the water, making little flashes of light. How do we know that these are really neutrinos and not something else? Because most of them, well, first of all, where do neutrinos come from? They come from all sorts of radioactive processes, anything that involves a neutron changing to a proton, any kind of beta decay. They come from cosmic rays, supernovas, and stuff falling into black holes, and violent stuff in space will create neutrinos, and nuclear fusion. So every star is making neutrinos all the time. But the closest one is the sun. So most of the neutrinos we detect should come from the sun because we're really close to the sun. And what happens in a neutrino detector like this is in the morning, most of the electrons are moving from east to west because they're getting kicks from the east. And at noon, most of the electrons are moving down because the neutrinos from the sun are kicking them down. And at sunset, most of them are coming from the west because the neutrinos coming from the sun are coming from the west. And at midnight, most of them are coming up through the ground because at midnight, the sun is down there on the other side of the earth, and the neutrinos are going all the way through the earth, kicking an electron in our neutrino detector and sending it upwards to the top of the detector. So we can actually see the motion of the sun across the sky as the earth turns on its axis, and see that the neutrinos are coming in the direction that the sun is coming from, or coming from the direction that the sun is at any particular time of the day. So we know that these neutrinos are coming from the sun, and that's how we know they're neutrinos, and that's how we know neutrinos exist. And that is how we know that nuclear fusion really is happening in the core of the sun, because we can see the neutrinos coming from that process directly, which is super cool. Oh, this is an even closer up picture showing the phototubes. You can think of the phototube as just a light bulb in reverse. Like, what does a light bulb do? You run electricity through it and light comes out. What does a photosensor do? Light comes in and electricity comes out the other end. So these are the technical name for these is photomultiplier tubes. They just take a little bit of light and convert it into an electrical current. There's another interesting neutrino detector that works on the same principle, but different construction. Instead of using liquid water, it uses ice. And instead of using a bunch of water, we've got to build a tank to hold. It uses ice that's already there. This is a neutrino detector called AMANDA. AMANDA stands for the Antarctic Muon and Neutrino Detector Array. And it uses the ice of Antarctica as the material that sits around and waits for neutrinos to hit it. Once you get, when you think of ice, you think of it as being kind of like cloudy and bubbly, like the ice from your refrigerator at home, right? Or a frozen lake. It's kind of cloudy and you can't see through it. But in Antarctica, once you get past about 100 meters or so deep into the ice, the pressure of that ice, it's as clear as glass. So AMANDA has got a bunch of the same photomultiplier tubes as are in Super Kamiokande, but they are located in holes that we have drilled deep into the Antarctic ice. How deep? Here is a picture to scale showing that this field here of detectors is about 2 football fields in diameter, and the depth of these holes is about 4 Eiffel Towers deep. Eiffel Tower is about 500 meters tall. So 2.5 kilometers deep are these holes in the Antarctic ice. We drop wires down there and we hang these photomultiplier tubes from the wires, and it creates a 3-dimensional array of photomultiplier tubes. So as an electron or as a neutrino hits an electron and that electron comes zipping through the ice, it gives off a little flash of light. And we detect that flash of light from the photomultiplier tubes. And if they trigger in a certain order, we can tell what direction the electron came from, right? Here's an event is what physicists, is the term physicists use for when they detect a neutrino. That's a neutrino event. And the time that the photomultiplier tubes trigger tell you that the neutrino was coming up in this case. So the neutrino was coming up through the Antarctic ice, having passed all the way through the Earth. And we can tell something about the direction of that neutrino and also make some guesses about its energy. But because we're not detecting the neutrino directly, because we're detecting it indirectly, we still don't know all of the details about their properties. Imagine you're watching a game of billiards, a game of pool, being played with an invisible billiard ball, an invisible cue ball. And you can watch the other balls bounce around, but you never see the cue ball that hits them. You can make some guesses about where it's coming from, but you can never quite know exactly where it's coming from because you didn't know exactly the angle that it hit the ball. And you can't tell how massive it is because you don't know how fast it was moving. You can make some guesses, but you'd be limited. For a long time, we weren't sure if neutrinos had mass at all. Like, do they have a tiny, tiny mass or do they have 0 mass? We weren't sure for about 30, 40 years. Come the 1990s to early 2000s, we're pretty sure that neutrinos do have a mass. We can put limits on that mass, but we don't know exactly what that mass is. So there's still a lot to learn about neutrinos and their properties. But for our purposes, for this astronomy class, the reason neutrinos are important is that they are direct evidence of what's happening in the core of the sun. The number of neutrinos given out and the energy of those neutrinos tells us something directly about how much fusion is happening in the core of the sun. And that is super, super exciting because those neutrinos go right through the sun without stopping and make it all the way to the Earth. Okay. Neutrinos are also created by other astronomical events like supernovas. Nowadays, so what's a supernova? First of all, we haven't talked about them yet. A supernova is a star that blows up. And usually it's a star that is super far away and we couldn't see it at all before. So the star just suddenly appears in our telescope that we hadn't seen before because it's just exploded and gotten a billion times brighter. Nowadays, when that happens, we see the star appear in our telescopes, but we also get a burst of neutrinos on that same day at that same time from our neutrino detectors. And comparing the energy of those neutrinos with the amount of light given off by the burst, we can learn something about how much energy is given off in these supernova explosions. So neutrinos are actually now tools for astronomers for deducing things about complicated processes thousands or millions of light years away. They give us a way to kind of peer into these complicated processes that happen in nature. Another thing that file the neutrino away in your brain for about 2 weeks, because when we talk about galaxies, we're going to talk about this idea of dark matter, this idea that there is some kind of stuff in galaxies that we can't detect directly, but we can detect the effect of its gravitational pull. This stuff is called dark matter. We don't know what dark matter is. But if I just said that every square inch of the room you're in is filled with trillions of neutrinos, and if neutrinos have even a tiny, tiny mass, they could be part of this dark matter. They could be contributing to the mass of the galaxy, even though we don't detect them usually directly. We don't see them. They don't give off light. When we look at a distant galaxy with an optical telescope, we're not seeing its neutrinos. But if the neutrinos add mass to the galaxy, we could see the effect of that mass on the gravitational attraction holding that galaxy together. So again, file the idea that the space you're sitting in right now is filled with neutrinos. File that away from when we talk about dark matter, because what we'll be talking about is the idea that every cubic inch of a galaxy might be filled with some invisible particles that we're not aware of. And maybe those are just neutrinos, or maybe not. So that's where we're headed eventually. I will go ahead and stop that there, I think. And what we will do next is go back to talking about nuclear fusion in the context of stars and start talking about, hold on, I'm going to switch back to Zoom here. Start talking about stars that are different from the sun, stars that are more massive, stars that are less massive, stars that are younger, stars that are older, and how this process of nuclear fusion might be expected to change over the course of a star's lifetime, and what the future of our sun might look like, what nuclear fusion in the sun might look like in another 5 billion, 10 billion, 15 billion years. Okay, so that's what's next.